Okay. Yeah, thanks for the super nice introduction, Nicole. So I'll talk about machine learning applications in collider physics. And to keep the overview, I will first give this small overview of like how you can use machine learning in this field. So broadly speaking, I think about the things that we do in collider physics as like either we take data from the measurements or we take them from our simulation, then we compare them and see if we find a difference ultimately. And people have started to develop a lot of machine learning applications, as you're probably all aware of, for a lot of essentially all parts of this simulation chain. And one thing that is common to a lot of them is that they operate on particles. So yeah, formenta essentially may be a particle type, and these particles have in common that they have that there's a notion of Lorentz symmetry that we can use as an implicit bias to improve our models. And with this L-GATr project that I will talk about today, we essentially developed a tool that operates on particles and that uses this Lorentz symmetry. And we designed it in a way to be super versatile and not only applied to chatting, where this is already very established, but also to other problems. And today I will talk about also amplitude regression and generative networks in the end. Yeah, and we're also working to establish this even more. So recently there was another work in our group where we use this also for simulation-based inference, and we're also working to use this for unfolding and maybe more things that we or you can come up with. So there's really a lot of applications for this tool. Okay, but before we go into all the experiments, I will for roughly the first half of the talk, explain how the L-GATr architecture works, and then afterwards we come to the experiments. So L-GATr stands for Lorentz-Equivariant geometric algebra transformer, and there are essentially three key ingredients. First, we use geometric algebra representations as an underlying language, which makes it easy to talk about all these symmetry things. And this language makes it then really easy to construct Lorentz-equivariant layers. I will explain later in more detail what equivariance means. It essentially means symmetry aware. And we then use these layers to construct and put them together in a transformer architecture that has all the nice scaling benefits that we know from, for instance, the very successful language models that are very popular these days. And this architecture is now for us for the Lorentz group, but it was originally developed for E3, the symmetry group of rotations and translations in 3 dimensions. And we then joined forces with the author of that paper to apply this to high energy physics. Okay, so what is geometric algebra? It's essentially a synonym for Clifford algebra, which maybe some of you have heard of before. It's a common concept in quantum field theory. But essentially what it means is you have a vector space and you extend this vector space by a geometric product. And this geometric product can be decomposed into a symmetric part, which you can think about like the scalar product of the space, and an antisymmetric part, which is the outer product and gives you all the new higher order objects, which were not there in the original vector space. And this is essentially what makes the geometric algebra so powerful. And we will talk specifically about a space-time geometric algebra. This is the specific example of having of the real 4-dimensional vector space with the Minkowski metric. And the basis elements of this vector space, they have to be orthonormal. They're defined by this orthonormality relation. Here, this anticommutator in red. And yeah, if I tell you now that this is an orthonormality relation, this is maybe a bit surprising because you don't see the inner product. But if you look back and see that the anticommutator was just exactly that, then yeah, this may be now a bit clearer. And yeah, this is also the relation that defines the Dirac algebra, which is used to describe spinor interactions in quantum field theory. Up to the slight difference that the space-time geometric algebra has is defined over a real vector space, and the Dirac algebra is a complex vector space. Okay, now we can start from these scalars, from the scalar that we obviously have, and the vectors. to construct higher order objects and map out the whole algebra. And the first step is to take the product of two vectors. We can decompose it into a symmetric part, which is just a scalar, as you would expect from a scalar product, and the antisymmetric part. And the antisymmetric part gives us now an antisymmetric tensor, which is 6 new objects. And we can take it even further, take the antisymmetric product of 3 vectors. This gives us 4 new objects, the axial vector. And finally, the antisymmetric product of 4 vectors gives us the pseudoscalar, which is 1 new object. And with this, in total 16 objects, we can expand any generic object element of the geometric algebra, which we call a multivector, in terms of these basis elements with some coefficients. And these coefficients can be used to characterize any object in the geometric algebra. And these 5 types of multivectors, if you want, so the scalar, the vector, the bivector, and so on, we call them the grades. And to make the connection to physics, a multivector representing a particle would be, for instance, that you take the momentum and put it into the vector part, and the particle type information goes into the scalar part. And if we have an application, we can also use the bivector and so on parts, but for in the simplest case, we can just set them to 0. And yeah, in practice, of course, we will have like then maybe 1 multivector per particle, or maybe even several multivector per particle if there's like more than one form, depending on the problem really. So this gives us a lot of freedom. Okay, so in real simple, usual neural networks have, for usual neural network, a channel is just one scalar number. And now for this geometric algebra network that we will have, one channel will be a multivector, so 16 numbers. And then all the architecture is now not operating on single scalars, but on these multivector objects. And they always stay in this form. But now before we go into how we construct all the layers, I will quickly explain what equivariance means. And for that, we first need the concept of invariance. So if we have an input to our network, which is some kind of vector, then invariance means that the output stays constant if we perform any symmetry transformation on the input. So for instance, let's say we have this input vector here in black, and then we have a not invariant model and an invariant model. And for this input, they now both give us the same number. But now if we rotate the input, then the not invariant model changes its output, whereas the invariant model keeps the same output. Now, how would you implement this idea in a neural network? In this case, I would say quite simple. You can do something like just building all the invariants that you can construct from your inputs. So of course, in practice, it's multiple inputs, not just a single one. And then give them to the network. And then the network operates only in invariant objects. And of course, the output will also be invariant. But what if you want to predict a vector and not just a scalar value? And now the concept that we're talking about is equivariance. This is the machine learning expression. In physics, we usually call this covariance. And this is a generalization of invariance. Equivariance can be with respect to any possible output type. It can also be that you predict a vector, a matrix, and then you want the matrix to transform. But in a simple case, we just look at predicting a vector based on a vector. And again, we have our input vector, and now the output vector is, because both the non-equivariant model and the equivariant model are the same, get the same output vector. But now if we rotate the input vector, then the output vector of the not equivariant model behaves really weirdly, somehow transforms, but not in the way we want it to transform. The way we want it to transform is that it rotates in exactly the same way as the input vector. And this is exactly what an equivariant model will achieve. And yeah, now the question is, how can we get that? And as we will see, the L-GATr architecture does this in a scalable way. There are a lot of ways to do it essentially, but the big benefit of L-GATr is that it's very, very numerically stable and easily scalable. Okay, but before we go into how we actually do it, a bit of formalism. What equivariance means in a more like mathematical sense. So essentially it means that if you take a Lorentz transformation and a null network transformation, these two transformations commute. So if you first do the null network and then the Lorentz group, this is the lower path in this diagram, then you get the same output as if you, based on some form momentum as an input, as if you first do the Lorentz transformation and afterwards the null network. And the way we do this in the GATr architecture is that we impose that each GATr operation transforms all the components within a given crate equally. So for instance, there could be one learnable coefficient in front of each crate. And the reason why this makes the GATr architecture equivariant is that each of these crates, so the scalar, the vector, the bivector, and so on, they all form sub-representations of G. So no information from the vector crate will go into the bivector crate at any point. The information in the vector crate always stays within the vector crate and transforms as a Lorentz vector, whereas the bivector transforms as a tensor. Yeah, that's quite formal. I will explain later on, give you really very concrete equations on how we do it. But first, I will quickly explain why we want to have a transformer with this. So essentially, transformers are combine three concepts. First, they implement permutation equivariance. So this is now a different kind of equivariance. First, the Lorentz equivariance we had earlier was like for continuous transformations. Permutations are discrete transformations. And the kind of data that we have, let's call it X, has two indices. It's just to visualize this. So essentially, the first index is this permutation index. So you can exchange X2 and X3 and in the input, and then in the output, they will transform in the same way. And then there's a second index, this index C, which is like the channel index. So this is where the null networks operates on. And the difference between the two indices is that the first index has can have any shape. So the network should be able to operate to process an input with 10, but also with 15 inputs, whereas the second input has a fixed shape. And then we take this input XIC, and the idea of the transformer is now to continuously update this input to obtain a better representation. And then in the end, we can map it to anything that we ultimately want, which could be, for instance, the tagging score of our chat tagger. And the way how transformers achieve this is that there is the very magical concept of attention, which uses this attention matrix, which I try to illustrate here as like a matrix, which essentially tells you which which element of the set is how important for which other element of the set. And then we do like a double matrix multiplication. So there is one matrix multiplication in this permutation index I. So this is the Aij, and this depends on X. And the second matrix is this W, which is a learnable matrix because C has always the same shape. This is like the high-level introduction to transformers, but now I will get a bit more in detail. So transformers are based on a set of operations. So for instance, the linear layer, attention layer, and the attention, this is now essentially the spelled out formula for what I had on the last slide, and then also layer normalization, activation, and a few more, which are not so important. And the idea of what we do with L-GATr is now that we build for each of these transformer layers a similar layer which in the transformer layers operate on scalars. And now we build an L-GATr layer which operates on multivectors. And we construct them in a way such that they do not violate the Lorentz equivariance. For instance, if we take the linear layer, then for the transformer, this is just a linear operation. And for L-GATr, we now have to be a bit more careful. What we do is we use this crate projection operator. This is the brackets. And if k is 0, this gives us the scalar crate. If k is 1, this gives us the vector crate, and so on. And then we just sum over our 5 crates. And each crate gets one learnable coefficient. This is the first term, and the second term is a bit more subtle. This implements that we are not interested in the full Lorentz group, which also includes parity and time reversal. For this project, we only want to do the fully connected subgroup, SO plus 1, 3. And the second term essentially allows the scalar and the pseudoscalar part to mix, and the vector and the axial vector part to mix, and also the bivector part. Now the second part is just optional if you don't want the full Lorentz, if you don't want this fully connected subgroup, but a full Lorentz group, then you would just drop it. And similar, we proceed with all the other layers. There's one subtlety or one benefit of the L-GATr architecture, which is we have this geometric product as an extra operation, and we can just add this as an extra layer, which is essentially another source of nonlinearity, or another activation function if you want. Okay, so that was the formal part. Now, in real simple, this is how we put together all the operations that we had on the last slide to get our full L-GATr architecture. So yeah, if you've seen normal transformer architecture before, this is super similar. Essentially, you have a linear layer in the beginning, in the end, and in the middle you have a stack of transformer blocks, and each transformer block has first an attention part and afterwards an MLP part. And essentially what we did compared to this normal transformer architecture is just replace all the non-equivariant layers with the GATr layers. And we add the geometric product as an extra operation. And yeah, now finally, this is a bit about, before we go into all the experiments, this is a bit about the scaling of this architecture. So on the left, we show the evaluation time of pushing essentially one bunch of particles through the network once, and then over how many particles we push through the network. And on the right, we have the memory usage of this architecture. And then we compare the L-GATr model with a normal transformer and also with a Lorentz-Equivariant graph model, which is, for instance, the CGENN. And what you see is that the evaluation time for the transformer and L-GATr are essentially the same if you have really a lot of particles, and that is because they use the same attention mechanism. But if you have few particles, then there is a factor of 5 or so difference, because the L-GATr model has a more complex linear layer. And it's hard to, principle may be possible to further optimize this linear layer, but we didn't manage to do that yet. But if you now compare the L-GATr model with the graph model, then you see that the L-GATr model scales a lot better. So it's for few particles, a factor of 10 or so cheaper. And also this takeoff, because at some point you have to exchange information between any pair of particles. At some point you run into quadratic scaling, and this takeoff happens much earlier for the graph model compared to the transformer. And a similar behavior is for the memory usage. Okay, that's the first part of the talk about the formalism. Now I will go into the experiments that we did. So first I will talk about regression, then I will talk about classification, and then I will talk about generation experiment, and they are all from parts of the simulation chain. And in all of these applications, we found that L-GATr essentially improves the state of the art compared to what we had before. So I'll start with amplitude regression. So here the task is that you want to, for your Monte Carlo sampler, you want to very quickly evaluate QFT amplitudes. And the problem is that if you are at if you have higher order corrections also, then at some point you will have expressions that you have to evaluate numerically, like polylogarithms or so. And this can become very expensive, even if you can really write down the analytic expression. And so in some cases, it can really help to train a neural network on this analytic expression. And then just evaluate the network, because evaluating the network is faster than evaluating some infinite sums. And in this task, we really have full Lorentz symmetry. Like these amplitudes can really look at the expression and see that this is fully Lorentz equivariant. So we looked at production of a Z boson and then plus extra quarks. And then we looked at how a bunch of architectures that we compared scale with the number of extra quarks, gluons, sorry. And we compared the most simplest approach is just an MLP. Then we can compare the MLP and a transformer. And you see that a transformer is already much better. And the reason for that is that the transformer implements the permutation symmetry in the process. So you can essentially tell the transformer that all the gluons are the same. And then for this reason, the transformer doesn't have to learn again how the amplitude looks for different gluons. Then the next step is comparing an MLP to what we call GAP, which is essentially an MLP that uses geometric algebra representations. This is the red line. And you see that there's essentially like a constant improvement. And this comes from the Lorentz-Equivariant that is built into this GAP model. And we have two other architectures, the SI and CGENN. They both implement some kind of Lorentz and permutation equivariance. But they have the same symmetry as the L-GATr model. But as you see, the L-GATr model is the most performant. Yeah. So there are two takeaways here. First, you want permutation equivariance in this application because this improves your scaling to the high multiplicities. And second, if you add Lorentz equivariance on top, then you get another constant improvement. And yeah, you might now say that the difference between a transformer and the L-GATr is not that big if you go to high multiplicity, but improving by a factor of 2 or so at this level is really a big achievement. Okay, the next application is chat tagging. Yeah, this is a very established application of machine learning in high energy physics. And I think one of the first big applications where machine learning actually helped. And here I will go a bit through the history and look at this top tagging benchmark. So it started in 2018, and then people tried a lot of different architectures, and the performance essentially plateaued at some point with these particle net and party architectures. Particle net is a message passing graph, and party is a transformer. They both implement the permutation symmetry that you have in this task. But then improving was a bit hard. At some point, there was this MI-party model, which essentially also is an improvement of party, but to my knowledge, it doesn't scale that well to, it's essentially a trick that you can do. What it does, it includes extra edge features in the architecture and process them in a specific way. And this helps a lot for top tagging, but from what I know, it doesn't help so much for other tasks. Okay, we have now these particle net and party, and then the next step in the evolution was to build models which are both permutation equivariant and Lorentz equivariant. And these are these green models. And there was first Lorentz and Pelican. They are both graph nets. And then we added the L-GATr model. And you see that they are essentially all on par with each other. So they use the full symmetry group that you have in the process, Lorentz symmetry and permutation symmetry. And so it's kind of nice check that they give you the same result. Okay, but now there's one subtlety in this application, which I didn't mention before. And this is that this chat tagging score that we want to predict with these models is actually not Lorentz invariant or equivariant. And there are two effects that break this, the Lorentz symmetry here. The first effect is just the topology of the collider. So there's this beam direction, and you can essentially only rotate around the beam, not so the z-axis, and not around the x and the y-axis. Otherwise, your beam changes. And second, you have you also break the boost invariance, and that's because of detector effects, and also just the geometry of the detector, and also because of chat algorithms, because they use PT, and PT is not invariant under Lorentz symmetries. So yeah, in practice, actually, we only have invariance here with respect to a subgroup of the Lorentz group, which is just the rotations around the z-axis. But yeah, as you've seen before, still Lorentz equivariance helps. And we'll also see this again later for the generator. So it's essentially you only have strictly only invariant with respect to a subgroup, but still having the implicit bias for the full group helps you or not, because you still have kind of like approximate invariance with respect to the full group. And yeah, these symmetry break. So yeah, and the symmetry breaking is present for all Lorentz equivariant taggers, and they all use essentially the same way to handle this. And the way we do it is that we add extra inputs to the list of particles. We call them reference particles or reference multivectors, because we embed all particles as multivectors, and they break the Lorentz symmetry. And for instance, we have like, for each kind of symmetry breaking, we have one reference multivector. For the beam, we have either a vector pointing in the beam direction and orthogonal to it, because there's a mirror symmetry, or we take a plane orthogonal to the beam. That's possible because these bivectors can be interpreted as planes. And for the boost invariance, we take a time, essentially a multivector pointing in the time direction. So why this works is because essentially the architecture is still fully Lorentz equivariant, but the inputs are fixed and they do not transform under Lorentz symmetries. So if you want, the architecture is still equivariant, but the inputs are not equivariant, even though they are vectors. Yeah. Okay, and now we can take this to the... So top tagging is nice. We can like benchmark a lot of architecture, but in practice, people are not training on only 2 million chats and have then like issues with regularization and so on. In practice, people train on really a lot of chats. So we also want to benchmark our model on that kind of data set. And we take this chat class data set for this purpose. And unfortunately, the other Lorentz equivariant models, which are all graph models, they have not been benchmarked on this data set yet. So we are the first. And yeah, now we can compare the different approaches. So as you see, ParticleNet, the graph model, is here significantly worse than Parti and MIME-Parti, the transformer models, even though on the top tagging data set, they have had the same performance. So it looks a bit like transformers. If you give them a lot of data, they can handle the data more efficiently, or they scale better to a lot of data than graph models. And if you now put the Lorentz equivariance on top and look at our L-GATr model, then we see that it performs even better than the non-equivariant transformer models. So that's really nice. And now the last step in the evolution, if you want, is to do transfer learning. So we have these really large data sets. So what we can do is we train the model on the large data set, then take the model and fine-tune it on this top-tagging data set and see if we get even better. And the result, super cool, is that this actually works. And you see these new boxy points for the fine-tuned models. So FT always stands for fine-tuned. And if you take the ParticleNet model, then you see that this only gives you a small improvement. This is kind of expected from the result on the last slide. But if you take the Parti model, then you see that you get really a big improvement. And similar for the L-GATr model. And yeah, again, if you combine both equivariance, Lorentz equivariance and permutation equivariance, then you get the most performant model. Yeah. Okay. That was it for the tagging part. And finally, I will talk about the generative model. So here we really want to go, we just specify the process, and then we generate reconstruction level particles, essentially unconditional. and we ignore anything that happens in between in the simulation chain. This is quite ambitious because at the level of the detector simulation, the event has like thousands of channels, but our network doesn't know about that. And it also like, yeah, we can fully ignore this, and we don't enforce that in between the model agrees with the simulation. This makes it much easier to train, but and also much faster. But yeah, maybe this is an issue with this approach. The dataset that we train on is two top quarks, which both decay hadronically, and then up to 4 extra jets. So this is, I think, already quite challenging. And then we have a full simulation, so MudGraph, Pythia, Delphis, and in the end, a reconstruction algorithm. And then what we want is to really get all the correlations that you can come up with in this up to 40-dimensional phase space correct. So the most challenging features in this data set are the invariant or the reconstructed masses of the top quark and the W boson. And then also, because these are up to 10 jets, they have a minimum angular separation, which is indicated here in this plot on the right. And this is like a clear artificial cut in your data set, and this is quite hard to learn with neural networks. And yeah, as you will see later, this is where the L-GATr architecture helps a lot. And similar to the chat tagging task, here we are also working on reconstruction level. So the Lorentz symmetry is broken if you want, and we have to use these reference multivectors to get the correct symmetry group. If we don't do it, then we get really bad results. Okay, so now how do we set up the generative model? We use continuous normalizing flows. The idea here is to connect a simple base density, which could be, for instance, a Gaussian distribution, to a complex target density, which is our physical phase space. And the connection happens through a differential equation, which essentially interpolates smoothly between the two. So if you want to go from the base density to the target density, then you just integrate over this differential equation. And it's a null differential equation because the velocity field in this differential equation is a null network. And now how do we train this neural network? This was historically a bit of a challenge, but essentially the answer is that we want to use conditional flow matching. The idea here is that you somehow specify a target velocity, which is conditional on the start and end point of your trajectory, and then you train a neural network on a regression objective to minimize the difference between this target velocity and the learned velocity. Or in other words, you like tell the neural network how it should connect the 2 points. And then the key point is that you force the network to learn an unconditional velocity. So there's no like unique solution to this task. This is actually a challenging task. And now the big question is, of course, how do we pick this target velocity? And the naive approach would be to just take your form momentum, so EPX, PY, PZ, of the like in the base distribution and in the target distribution, and then you interpolate linearly between the two. So you change E linearly, PX linearly, and so on. But this doesn't work so well. What works better is if you use this modified representation, X, which is obtained with this log transformation and phi eta. So these are just phi is the azimuthal angle, eta is the pseudo rapidity, and pt is the transverse momentum. And the advantage of this X parameterization is that it automatically takes phase space constraints into account. So on the right, you see in the px py plane how the straight trajectories in this X coordinates look like. And what you see is there's this forbidden region if your transverse momentum is below a certain value. That's just because of how the chat algorithm works. And you see that the trajectories nicely go around this hole. And if you used the normal momenta P, then you would just have straight lines in this space, and there would be trajectories which go through this forbidden region, and it would be hard for the neural network to learn this phase space cut. And we also did some studies on how this affects the performance. So the first line in this table is you take the naive parametrization, the momenta, and then the very powerful L-GATr architecture, and you see that the negative log likelihood of this model is quite large, which is bad. Or if you want, the likelihood is small. And this is the likelihood of the model giving likelihood of the data of the test data set giving the model. So this is a very common performance metric for generative networks. So yeah, we conclude if you take this naive momenta and be straight in them, then you are quite bad. And if you go instead use the smarter X representation and a simple MLP architecture, then you're already a lot better. And then if you combine all ingredients, the L-GATr architecture and the smart representation, then you end out on top. And we also do 2 tricks here, which is first we do rejection sampling in the base distribution. This means that we essentially, like there are these delta R for these regions which violate this delta R cut. And when we sample points from the base distribution, we directly neglect points that violate this constraint. And second, we build the periodicity in phi into how we construct these trajectories. So if you are at pi minus epsilon and you want to go to minus pi plus epsilon, then you don't go the long way, but you go the short way around the edges. Okay. And so now we know how we want to choose our trajectories. The next step is how do we construct the velocity field? So we start from our x, this is essentially the phase space point, and now we want to compute the velocity at this point x. And the naive approach, if you had a non-equivariant model, would be just to put x into the neural network and extract the velocity. Super easy. But the problem with the L-GATr architecture is that L-GATr only takes momenta as inputs. So what we do is we first transform our x into the corresponding momenta p, and we use the transformation f to do that. And then we put p into the L-GATr architecture and extract the velocity vp. So this is a velocity referring to momenta. But we want vx. So what we do is we multiply with the Jacobian of this transformation to get the vx. And now there's one problem with this approach, which is if the f transformation contains a logarithm, then this Jacobian can blow up and we get a really unstable training. So what we do to avoid this is we extract the problematic velocity components, which are the xm and the xp velocity components. These are the two with the log transformation. And we extract them from the scalar output channel of GATr and then use them to override the equivariantly predicted channels. And then everything trains in a stable way. And you can think about this essentially as, or this is effectively another way of breaking the symmetry in addition to the reference multivectors that I talked about earlier. But it's really breaking the same symmetry because XP and XM are both invariant under the subgroup that we do not want to break. Yeah, so this is really a redundant symmetry breaking. Okay, this is all for the formalism. Now we can look at some results. These are the simplest thing to look at, just kinematic distributions. And now we compare the MLP, an MLP velocity field, a transformer velocity field, and our L-GATr velocity field. And you see that in all 3 plots, the L-GATr velocity field is a lot better. And I have a lot of, there's a lot of plots like this that you can draw. If you want, I have a lot of them in my backup material. But essentially, L-GATr, you clearly see it's always better. And it's especially clear in this plot in the middle, which is like the angular separation between two jets. And here you really see that the L-GATr model learns it to like percent level precision, whereas the other models really struggle to learn this clear cut. It doesn't help so much with the reconstructed top mass on the right, and that's also kind of expected because the top mass is invariant under Lorentz transformation, whereas the delta R has a very complicated transformation behavior. Yeah. We can also look into a more global metric. So here what we do is we train a neural classifier to distinguish generated events from proof events. So if the generator is perfect, then the neural classifier cannot distinguish the two, and we get an AUC of 0.5. And you see essentially the same hierarchy as we had in the last slide. MLP, then transformer, and L-GATr is the best. And it's also really nice to see that the L-GATr model has an AUC of very close to 0.5. And that means that that essentially not even a neural network can distinguish the samples that we trained with our GATr model. Okay, it can distinguish it a bit, but it's already really hard for it. And that even though we train on quite hard tasks. Yeah, so that's a really nice result that there's no obvious failure mode of these models because of the classifier would find that. And now finally, we can ask the question why does the L-GATr model so much better than the transformer model? And to study that, we trained another GATr model, the E3 GATr. So E3, if you remember, is the symmetry group of rotations and translations in 3 dimensions. We actually don't care about translation, so you can also call it the O3 GATr model for this case. And what you see is if we train also this model, we get essentially the E3 GATr and the non-equivariant transformer. They are essentially give the same performance. Whereas the L-GATr model is much better. And this is very interesting because it essentially means that it's the boost equivariance that gives us the performance, not the rotation equivariance. But if you recall, the boost equivariance was actually broken in the L-GATr model. Or more exactly, the L-GATr architecture is boost equivariance, but the network inputs are not because of these reference multivectors. Whereas in the E3 GATr, there's no boost equivariance at all. So the nice message here is that it's really about how we break the symmetry. So even like in this case, we have broken symmetries, but they're still kind of like approximately valid. And if we build this approximate validity into our neural network, we benefit a lot. And I think that's the most exciting result from this study for me. Okay, this is now about takeaways. So we built this L-GATr model really as a multi-purpose architecture for LHC physics, not just chat tagging. Can do a lot more with it, and you're very invited to think about possible applications. And we're also working on that, of course. Then the symmetry breaking is super important in LHC physics because in most applications it's broken. So we have to reflect that in what we give to the neural network. Then we saw that in chat tagging, we can get the up-to-date, as of today, essentially the best chat tagger if we combine the benefits from Lorentz equivariance with the benefits from pre-training, where transformers benefit a lot, and L-GATr comes out on top. And finally, we looked into Lorentz equivariant generators, and we saw that they really help. And maybe I didn't stress this enough in the talk. The cool thing about Lorentz equivariant generators is that you really need an equivariant model, whereas for the amplitude and the tagging models, invariant models are enough. But with in the event generation task, you really predict a vector field, and this has to then transform correctly under Lorentz transformations, and this is what we get from L-GATr. So here we really use it in a very non-trivial way. Okay, then I want to quickly advertise our code base. So we put a lot of effort into designing it in a way such that it's easy to access for others. So it's well documented, and yeah, we included a lot of tests, so you can really check that the outputs of L-GATr are equivariant to like 10 to the minus 5 precision or so. And finally, I want to thank my collaborators and again invite you to check out the code and try to use the L-GATr architecture for your own task. Thanks.